Morning, everyone. Greeting for all of you. My name is M.bari A-1906357010-Final. So today I'm gonna present to you about my final project. Okay, let's enjoy. The first one, the title of my final project is Calculation of Anchor Terminal Velocity in the Water and Ensure Dropper Height using MDM technique. So the first one we must know it what is anchor. Anchor is the device, usually of metal, attached to ship or boat by a cable or chain and lowered to the seabed to hold the vessel in a particular place by means of hook or pointed projection that dig into the sea bottom. So the abstract for my final project is I got from a journal. So when anchor is dropped into the sea, three exist a danger of collision on the pipeline and subsea cable in the seabed. This collision could cause hook environmental disaster. In order to secure the safety of subsea structures such as a pipeline and subsea cable from the external impact, it is necessary to estimate the exact external force through the anchor terminal velocity underwater so we could know where is the anchor is dropped. To estimate the exact internal force through the anchor terminal velocity on the water, computational fluid dynamic program or CFD was used to accurate the terminal velocity and drag coefficient computation. And for introduction of my further project, many ships sailing in the sea use a various anchors. Since ships are becoming larger, the size and weight of anchor are also increasing. As a result, the risk of collision of subsea cable or pipeline that run for oil and natural gas is rising. Before we know the condition of collision analysis, we could use a model of three different anchor. I use three different weight. The first one is 525, 10.5, and 54 weight of the anchor itself. So we can use CFD. We got a drag coefficient and terminal velocity for every weight. For the weight 25, we got a drag coefficient of 0.8, and we can use the another drag coefficient and terminal velocity in this table. After that, we must modeling the anchor. Then the before slide we already got the weight and drag progression. So I can at this in this place I use a model to view the front, side, and bottom of the anchor itself. We can see in this shape of stock lock anchor. After that, we numerical modeling from the flow field and analysis condition. For the numeric analysis, the CFD program slide 30 was used. A flow field was formed with a volume of fluid or V of F model consisting of air and water, and the falling of the anchor from the air into water was simulated. For the numeric analysis, tetrahedral mesh were used. This mesh simulate the moving boundary flow in the MDM method. Furthermore, many elements were used to accurately simulate the stranding of the anchor boundary in the flow field. For a flow analysis, the boundary layer must be defined by the calculating the Reynolds number. Before setting the analysis model, the following equation was used to calculate the Reynolds number. We got a density, we got a volume, light, and the coefficient of weight itself. Right. In the next class, we can use MDM method to analyzing physical phenomena considering determination of a mesh or model was used. We could see in this height or 5-meter height of the sea bottom sea, we can know that the anchor is dropped in not in a velocity state. So, but the velocity state we got in active 5 of the height itself. So after that, we could get a weight of area and volume of the anchor itself. For the weight of 25, we got the area of 139.3 and volume of 0.696. And the another weight, we got the area and volume itself. You can see in this table. So after that, we assumption of the terminal velocity equation. For all of you know, when object falling in fluid such as water on recurve buoyancy and drag force acting opposite the moving direction, in general, resistance increase at a higher velocity, and when the object reaches a certain velocity, the size of drag force and gravity become equal, and the resultant force on the object becomes zero. As a result, the object moves at the uniform motion without acceleration. The constant velocity at which the object falls without acceleration after resting it is called the terminal velocity. So from this equation, we could know the height of the anchor itself. For the first thing, we must do the drag force of the anchor. We could get from CD or coefficient drag and we got density, area, and volume. We could get the drag force of the anchor itself. After that, we can use the second law of Newton to get the velocity itself. We can see it in this stage, where is we got the velocity itself. After that, we can use the law energy of energy, so we could get the height of the anchor itself. After that, we can see that this is the time when the anchor is dropped. We can see in this model, the first one is 1 second, it reaches 5 meters, and after that, the 3 second it reaches this height, and when the 7 second it reaches this height. So we get the result and comparison of the analysis. We got a velocity and the coefficient of 525 ton anchor. We could see the velocity is higher and then dropped slowly and stagnant. And the coefficient itself is 2. We can see itself in this graphic. And the 55, the 10.5 ton of anchor, we can see the same graphic. We can see that it reaches 47 meter per second for the velocity in a stagnant pace. And we get the coefficient is 134. And we get the velocity of 55 ton anchor, and we can see is the graphic look the same for the two before. And the terminal velocity, we can see that the higher of the height of the anchor, the higher the drag coefficient itself. We can see, and we can see in this graphic. After that, we got the calculation of drag height from Anselmo experiment. From the height of 525, the terminal velocity is 6507, and drop height of onshore experiment is 186.4. And the 95, we get the terminal velocity and drop height of onshore experiment 2. And with the height of 35, we get the terminal velocity and drop height of the answer experiment 2. So the conclusion about my final project, the 525 10 on 10 5 ton and 554 ton answer drop at 5 above the level of the terminal velocity of 60 40 4004 and 7 624 and 190 meters per second. Respectively, and the coefficient of 141 for 134 for and 100 322. This ratio suggests that the cross the force escape the case at anchor and velocity increase. Based on a numerical analysis, the 5 to 5 ton, 10 5 ton and 50 ton anchor have drop height of 186 for 200 170 m and 300 7 m respectively in the onshore experiment. So thank you for listening my final project. Thank you for attending it. Thank you for everyone that already see my final project. Thank you.